So, hello. I think some of us are very tired. Shall we wait a little longer until they come back?
Biraz atomikle atomistik aynı şey mi, farklı şey mi?
Atomistic yaklaşım.
Ha, ama atomik değilmiş.
Atomistic diyorum ama.
Öyle.
Metotskili var mı? Metotskili var. Yani, so, just a second. I have to do something here. We will start with the introduction to atomistic model modeling techniques. And as you know, by now, from the quantum treatment, ideally for an eight-particle chemical system or biochemical system, we have this equation. In practice, the full quantum treatment of the system is virtually impossible for obvious overwhelming computational reasons. At the Hartree-Fock level for n atoms, the CPU investment is gross O to the n to the 3. One possible solution is linear scaling approaches or divide and conquer growing SON. Currently, they are limited to small systems with a sampling of few picoseconds. Moreover, they are restrained to the Born-Oppenheimer approximation and are significantly more costly than molecular mechanics. So, in the Born-Oppenheimer approximation, we saw that the motion of the electrons and that of the nuclei are dissociated. The de Broglie wavelength associated to a given particle is substantially smaller than the intermolecular distances in a liquid. And quantum effects can be globally neglected. It is therefore legitimate to turn to the classical equations of motion in molecular dynamics simulations. Time averages and ensemble averages coincide for ergodic systems. And we turn to molecular dynamics simulations to access the atomic detail, not always accessible to experiment. Just a second. Yes. To gain dynamic information and to predict thermodynamic and kinetic properties. Molecular dynamics simulations rely on the equations of classical mechanics and therefore are restrained to the motion of the nuclei. They are limited to the description of molecular assemblies that do not involve the creation or rupture of chemical bonds. Ergodicity implies coincidence of ensemble and time averages and hence of properties inferred from Monte Carlo and molecular dynamics simulations. So when we consider a world from nano to macro, we start with the atomistic scale. We go to a nanoscale, which can be, for example, collagen fibers or proteins. And then we can investigate the dynamics of fracture in protein crystals or crack dynamics at the macro scale level. Okay, and we can combine them all. How do I do that? So biomaterials, biomolecules, right, consist of atoms. Depending on the scale looked at biomaterials, these atoms are visible or not to the eye or to the microscope that we are using, depends on the microscope. Nevertheless, the atomic structure always plays an essential role in determining biomaterial properties, in particular under certain conditions. So the structure of a complex biological materials and the levels of hierarchies are demonstrated here. And the problem, how can I? There we go. The problem is that we want the accuracy of quantum mechanics, right? And we want it for large number of systems, atom systems, like 10 to 23. It would be wonderful to have the quantum mechanical accuracy or quantum mechanical accuracy for such large systems. Well, this is impossible today and in the foreseeable future. A possible solution is multi-scale simulations. What are multi-scale simulations? These are based on modeling techniques, which in turn are based on hierarchies of overlapping scales. So when we come to this graphic here, we start with the microscopic level. We have quantum mechanical calculations in which reacts FF. We can go into molecular dynamics simulations, for example, which is the classical mechanics part. And from there on, we can parameterize from using our molecular dynamics simulations, the parameters, and then we can go to mesoscale simulations and then to macroscale calculations, or vice versa. From top to bottom, we can go from macroscale to quantum mechanics. And the bridge between them is represented by the blue color. Okay. Now, the time and length is demonstrated here too in this graphic, as you can see. And when we look at the history, how can I get rid of this? Yeah. Okay. In the 1600s, Da Vinci, Galileo Galilei started in the 1700, 1800, Euler, Bernoulli. They started the beam theories and Roth's partial differential equations, continuum theories. And continuum mechanics theories started, the development of the continuum mechanics theories were started. Of fracture mechanics, theory of dislocations in the 1930s, in the 1960s to 70s, development of finite element theories and methods by engineers, right? In 1990s, the marriage of molecular dynamics and finite element via quasi-continuum method by Ortiz, Tegmark, and Phillips. These are the continuum models. In the 20th century, well, atoms discovered, right? Molecular dynamics was first introduced by Elder and Wainwright in the late 1950s. They studied the interactions of hard spheres. Many important insights concerning the behavior of simple liquids emerged from their studies. 1964, when Rahman carried out the first simulation using a realistic potential for liquid argon. Numerical methods like DFT with Cohn-Sham, you are familiar with that by now, were introduced in the 1960s to 80s. First molecular dynamics simulation of a realistic system was done by Rahman and Stillinger, and they simulated liquid water in 1974. The first fracture and crack simulations were conducted in the 1980s and the 1980s by Gibb and others. And large-scale molecular dynamics simulations in this area were conducted in the 1990s by Aquaculture. So these were the atomistic models. Now, in these simulations, molecular dynamics simulations of biophysics problems, fracture, deformation, are routine nowadays. The number of simulation techniques has greatly expanded. Many specialized techniques for particular problems, including mixed quantum mechanical classical simulations, which we call QMML, that are being employed to study, for example, enzymatic reactions or transition metal line, protein interactions, etc. So molecular dynamics simulations, what are these? Molecular dynamics is an attempt to solve the classical equations of motion for a system composed of atoms and molecules with the aim of obtaining the time evolution of the system. Most often applied to condensed phase systems, that means solid or liquid state, where the objective is to learn about how the bulk properties of the system arise from the molecular basis. It's different than the Monte Carlo method, in which the molecular system evolves through a stochastic or random walk process, rather than a true dynamical process. This gives time-dependent properties such as diffusion, thermal conductivity and viscosity, or aspects of spectroscopy such as solvation-induced spectral shifts, or the kinetics of a biochemical process. So when it comes to NV simulations, I already mentioned de Broglie, but what that molecular dynamics describes the time evolution of molecular systems using classical mechanics is perhaps unexpected. After all, the atomic scale is the scale where quantum effects are supposedly important. In most applications, this is not a huge problem. The matter is determined by the thermal de Broglie wavelength of the atoms at the temperature of interest by using this relationship, whereby H, we know these constants by now, we had that in quantum too. H is the Planck's constant, Kb is the Boltzmann constant, and T is the temperature. And beta is equal to 1 divided by the Boltzmann constant times temperature. The wavelength is very often small enough for the atoms to be regarded as classical, meaning that no significant diffraction effects or quantum tunneling is expected. So this is an approximation, and we will talk about that more later, but nevertheless, it is prudent when dealing with lighter elements, in particular hydrogen at low absolute temperatures. There are time-dependent methods for dealing with systems that manifest quantum behavior, but they are hard to interpret. Classical molecular dynamics is preferred. If time dependence is unimportant and the focus is on thermodynamic and structural properties, the PAD integral Monte Carlo method is one of the best many-particle quantum methods available for the condensed systems. So, molecular dynamic simulations are numerical in their nature, and it's a computational method. The equations of motion are cast into a discrete form, such that knowledge of the atomic positions, velocities, and forces at a time t allow the determination, or better said, the estimation of the position and velocities at a short time, t plus delta t. Okay? This is referred as a time step. A typical simulation is between several thousands and several millions time steps in duration, so it takes a long time to conduct these simulations. The number of atoms in a simulation can range from a few hundreds to a million. The huge computational demand is clear. The time step is usually between 1 and 10 femtoseconds. And how many seconds is a femtosecond? Yes? Recommend 15 seconds. So it's really a very small time step. And you go from femtoseconds up to a second, for example. You do so many calculations in molecular dynamics applications. Bewildering amount of data is generated, right? Because you save the trajectories. And three-dimensional space of all atom, and often the atomic velocities, forces, and associated thermodynamics, such as energies and pressures, are created by your molecular dynamics simulations. Best practical option to deal with that huge amount of data is statistically, so that average properties of the system can be obtained, and this can be done by statistical mechanics. So we can use Boltzmann averaging. That means results are obtained by time averaging the data from a single simulation over a long period of time. or Gibbs averaging, which is different, meaning results are an average over many distinct but equivalent replicas of the same system at some instant of time. So MD is not without problems or limitations. For example, it's reliant on empirical data, most particularly in the description of interatomic forces, which we will see. It's a potent experimental tool because it's often providing insights and data that cannot be obtained in any other way. For example, we talked about the protein in water, right? And experiments face challenges, right? We said X-ray is in solid state and MR is for small proteins. Not large size proteins have an issue, and intrinsically so proteins are difficult anyway. And so experiments face issues, and molecular dynamics simulations complement experiments actually usually. And that's why it's a potent experimental tool for many people. So the model system, as you can see here, can be different. You have the ions, you have the protein, you have the water molecules, you can have the lipid, or you can have some other biomolecule of interest when you are interested in biology. The box is called the simulation cell. It's a cell. And the walls of the cell are not solid. It's virtual, right? It's in a computer. They are virtual walls, which define a unit of repetition in three-dimensional space called the periodic cell, which is the basis of periodic boundary conditions. So what are periodic boundary conditions? Now, if I had a solid cell with solid walls, it would be difficult to have, for example, energy exchange controlled on the temperature, right, on pressure, the number of particles. So how do I do that with periodic boundary conditions? So we want to bridge the macroscopic or the mesoscopic world to the microscopic one. These are water molecules, and here you have the water. Can we relate the properties of a system containing a number of particles on the order of NA to those of a system containing only a few hundreds or a few thousands particles? How can we handle edge effects? So, the periodic boundary conditions, what is that? So the blue one is the periodic cell that we just showed, for example. It can have your protein, it can have your water molecules, it can have everything. But the periodic cell is assumed to be replicated in the same way as a unit cell in crystallography, with the effect that the whole of space is filled. Atomic velocities are indicated by the arrows attached to each atom. Here you see the arrows. This system is in fact infinite in extent. So this is just a subsection of the whole, this picture, right? You don't have only 9 boxes there. So each cell shown is an exact replica of all the others, so the contents and dynamics of all cells are the same. We therefore need only pay attention to one of these cells, such as the shaded central cell, the blue one, and we need only to describe the dynamics of the atoms in this cell to describe the motion of all the atoms in the infinite system. So when you look at this picture, you will notice, since the walls are virtual, so for example, this one is coming from this box to this box, right? It's wandering around. But if I had here a solid ball and here a virtual ball, and this would move in, the number of particles would change in the blue box, right? We don't want that. So when this one moves in, The same one here on the other side moves out with the same velocity. Okay? Can you see that? The number of particles stays constant in my box, depending on the ascent. So here, for example, where else do I have that? Here, for example, it's moving in, it's moving out. Or here, you see how it's moving. And this is the periodic boundary condition. And the cutoff values, we will talk about that too. So this follows naturally from the fact that all images of a given particle have the same arrangement of surrounding atoms, which gives rise to the same forces and the same dynamics. Should an atom leave the cell due to the dynamics, an image of the atom with identical dynamical properties enters the cell on the opposite side, and the contents of the cell remain unchanged. Okay. Since the objective is to study the properties of the bulk system, not one unduly affected by surface forces, which are known to be strong. So if I had solid walls, I would have surface forces, right? So that would be different. Of course, in a real system, this precise periodicity is absent. Even in a periodic crystal, the instantaneous positions and velocities of the periodic image atoms are not the same. And this sets some spatial limitations on the properties that can be calculated. It is worth noting that there are many possible forms of periodic boundary conditions besides the simple cubic periodic boundary conditions that I just demonstrated. So here you have the cubic one. Simulations without periodic boundaries are also sometimes. Okay. So we set the interatomic potential, and here is the relationship. The atoms in our system are, of course, interacting with each other. So let's consider this system, for example. The atoms in this system are interacting with each other. And this is expressed in terms of an empirical pair potential, which we call Lennard-Jones potential. This potential is a function of the distance Rij between the two atoms, and I will explain what this Lennard-Jones potential is now. So Lennard-Jones potential, the first term is the repulsive potential, and the second term here is the weakly attractive force. Sigma, it has a unit of length, epsilon has a unit of energy, Vr is the interaction potential, and R is the distance between the centers of two atoms or two molecules. So when you calculate that, or when you measure that, you have this interaction potential, it yields this curve. And where it coincides with zero, here, it defines my sigma, which is the length here. And the depth defines my epsilon value. Okay? And after some time, after some distance, you see that it's approaching less and less changes. And that's where we can put the cutoff value and say, after that point, I don't need to estimate the intermolecular interactions using the Lennard-Jones potential. The first represents the repulsion experienced by the atoms when their electronic shells overlap, and the second represents the so-called London dispersion interactions. And this is in origin, actually, quantum mechanics. Okay. So the Lennard-Jones potential, when we talk about it a little bit more, a key point to stress here is that the interaction is a pair potential. But we have more than two atoms and more than two molecules in our system. Every atom is deemed able to interact with every other through such pairwise expressions. The possibility of a collective or many-body interaction is set aside as an unnecessary complication. This assumption proves to be valid one for the system, but for systems, for example, metals, this is not a safe assumption. The adoption of pair force potentials means that the maximum number of interactions we must evaluate in a system composed of n atoms is equal to n times n minus 1 divided by 2. Right? Therefore, the order of complexity of the simulation is said to be n, which is the highest polynomial dependence of the simulation on the number of atoms and is a good indicator of what the computational cost of the simulation will be. When it comes to the potential cutoff, here, this cutoff value here, for example. The potential, in principle, pair potentials have infinite range. No matter how much the separation between the atom pair, the potential has a non-zero value. However, it is found that for potentials like the Lennard-Jones potential, the value becomes negligible once the separation gets beyond a few multiples of the distance sigma. So it is usual to apply a cutoff condition for any pair of atoms separated by a specified distance, which we call our cut, which is our distance, cutoff value distance, cutoff distance. The interaction is assumed to be zero and nothing is calculated. So then we have the minimum image convention. Okay, this is the minimum image convention. I will explain that now. When using a cutoff in conjunction with a periodic boundary condition, it is usual to set the cutoff so that the net interaction experienced by each atom includes contributions from only one image of the other atoms in the system. This is known as the minimum image convention. Only the closest images of any two atoms contribute to the calculated energy and force. This is primarily an operational choice, since using more than one image makes handling the periodic boundary condition more complicated and therefore computationally more expensive. So here you have that case. So when you do your MD simulations in NAMD, how many of you are familiar with NAMD? It's like Romex or Charm or Ember, a program, a software package, NAMD. It's a nice one actually too. And you can use that too. This is how you give the cutoff value here. And here in this case, it's 9 angstrom. Okay. So the spherical truncation is acceptable for electrostatic interactions when n is larger or equal to 3, considering Rn. For n less than 3, an appropriate treatment is required, and this could be Ewald sum method or let method, Ewald and let methods. Okay. So using VMD or Chimera, but using VMD actually, when you use NAMD and VMD together, that could be a nice option to conduct simulations as well. We saw that with Romex, but this is another way, and I wanted to show that to you. You load the topology and Cartesian coordinates, right, of the biological object, solvate in a pre-equilibrated solvent cell. So here you see that the box size is defined as minimum and maximum, and you can define that for NAMD actually. And then you add the ions to a solvated protein ligand complex, for example, like we did. And it's important when you do that to think about the salinity at which the experiment was carried out, what ions were used, and what is the excess charge of the complex. So you can define all of them in NAMD using EM. So, or you can build a membrane protein assay. You can have an equilibrated membrane patch, insert randomly additives, insert even a membrane protein, add water if necessary, and insert ions if necessary, and the system becomes huge, but such simulations are conducted. So how many of you are familiar with charm GUI? One person. Okay. So it's a web-based graphical user interface to generate various molecular simulation systems and input files. Currently, Charm GUI supports Charm, NAMD, GROMACS, EMBER, and OpenMM simulation programs, mostly based on the Charm course. It was developed by Martin Karpus Group at Harvard, and he received the Nobel Prize, actually, for simulations. So this is a book that I would like to recommend. Get the structure from Protein Data Bank, as we did. You select the chain and molecule, you make a structure check, visualize and check again. You can introduce point mutations, for example, if you are interested in genetics or protonation state, you can play around with the protonation state, that means pH of the system, right? And then solvate it, set salt concentration, select the simulation protocols, which I prepared for you. But I would like you to look at these MDP files that you downloaded to understand the simulation protocols, actually. Prepare the simulation files, run the simulation, and then you can do a live analysis or an advanced analysis of trajectories. When it comes to the synopsis of a molecular dynamics simulation, you start with the point data, compute the energy, compute the forces, which are intramolecular, intermolecular, and constraints. And then it goes to the integration of trajectories and computing physical quantities that can mean intermediate averages, which would mean also compute again energy and compute forces. It's an iterative process. Or you can stop, and results and analysis of trajectories can happen, and you can analyze dynamic or thermodynamic properties of the system. So when it comes to the interatomic force, the pair potential gives rise to a force acting between the atoms I and J. The force on the atom J due to atom I is calculated as a derivative, as expected, right? The pair force obtained from the Lennard-Jones potential can be rewritten in this form then. And the pair force here is not the full force acting on atom J. So you need the sum sign. All the other atoms within the cutoff range, right, which is determined by the Lennard-Jones potential of atom J, will also exert a force. The net charge, the net force acting on atom J is the vector sum of these. So when it comes to the equations of motion, we can apply Newton's equations of motion to determine the subsequent motion of the atoms. We are familiar with these ones, I guess, from physics, right? Which was a prerequisite for this workshop. It needs to be rewritten in discrete form for molecular dynamics, and we can use, for example, the leapfrog algorithm to do so. And we can say the force at n time step is used to update the velocity at the n-1 divided by 2n time step to the n plus 1/2 time step, which is a time interval delta t, which we will see later. The position of the n time step is updated to the n plus 1 time step using the velocity from the n plus 1/2 time step. The calculation of the new atomic positions then allows a fresh calculation of the atomic forces from which a further step in time can be taken. So common assembles that are used in molecular dynamics simulations are microcanonical assemble, canonical assemble, isothermal isobaric assemble, and the grand canonical assemble. In the microcanonical assemble, you have the number of particles, which is n, the volume, which is v, and energy E constant. What is changing when NVE is constant? Pressure. Yes. What else? When pressure is changing, which thermodynamic properties would you expect to change? Temperature. Yes. What else? Enthalpy. Yes. So the canonical assemble is an assemble where the number of particles, volume, and temperature are constant. Which one is changing? Which properties are changing? Give me examples. NVT is constant. Pressure can change, right? Energy can change. Enthalpy, entropy, free energy, chemical potential, all these can change. The isothermal isobaric assemble, it's an NPT assemble. Number of particles, pressure, and temperature are constant. What is changing? Well, what else? Energy can change. Right? The grand canonical assemble, you have the chemical potential, volume, and temperature constant. What is changing? Pressure. What else? You can use it actually to draw the phase diagrams, you know? Yeah. So when we take, for example, the canonical assemble, the partition function, which we saw yesterday, is defined in this way, right? From the partition function, you have the de Broglie wavelength, number of particles, the thermodynamic potential, and it depends on number of particles, volume, and temperature that are constant. So it follows that the probability of finding configuration Rn is given by exponentially minus beta mu Rn. The thermodynamic potential of the canonical assemble is the Helmholtz free energy. It is derivable from F is equal to U, which is the internal energy, T is the temperature, and S is the entropy, and it's related to my partition function, actually, right? So here is a book, which I like a lot. You can learn molecular dynamics simulations with it. You can really run your simulations after only 1 day of training. So follow the trajectory of an assemble of particles with time, right? You can calculate the forces, and the forces rely upon potential energy function capable of describing the chemical system. So this is given by these equations. So typical time scales explored in molecular dynamics and computational resource required to access them are from picoseconds to second. And that's the time scale. And it goes from 1 gigaflop to 1 teraflop to 100 teraflops and 10 petaflops, okay, depending on the simulation time and system size that you are interested in. You can use also Lagrange equation of motion, Newton's equation of motion, or Hamilton's equations of motion, okay? Where we stand now is for 1 second, up to 1 second of simulations, we can study 10 to the 3 number of atoms in molecular dynamics simulations. And blue borders was a big one. for femtoseconds or picoseconds or nanoseconds, we can study smaller, larger sizes of systems. So, in its simplest acceptation, molecular dynamics consists in solving the Newton equations of motion using small time increments. Choice of the time increment is dictated by the fastest vibration in the molecular assay. Discretization errors are bounded provided that a symplectic integrator is used. Current molecular dynamics simulations attain the millisecond time scale and the 100 million atom size scale. So when it comes to the potential energy function, modeling a complex reality with a rudimentary toolkit, how is that possible? Here are some papers that you can read. And the potential energy function, modeling a complex reality with a rudimentary toolkit, well, you have the bonds, you have the angles, you have the dihedrals, you have the Coulombic interactions, you have the van der Waals interactions, etc., etc. What is a dihedral? How many know what a dihedral is? What is a dihedral angle? One person knows. So if you have 4 atoms or 4 molecules, right, and they are bound, there is no whiteboard or blackboard, so I cannot sign that, but let me sign here. Let's say you have 4 atoms that are connected. Here you have a plane, right? Here you have this angle here, how these planes rotate, is the dihedral. It requires at least 4 atoms. Okay. So my potential energy function depends on bonds, angles. Angle requires 3 atoms, right? And dihedral requires 4 atoms. And electrostatic and van der Waals interactions. And there are different potential energy function definitions in different force fields. And using the Ember force field, it looks like this, a harmonic potential. A harmonic potential was used to estimate the dependence on bonds, valence angles. Torsions is another name of dihedral angles. So you need again 4 atoms and its rotational planes. And we have the van der Waals Coulomb terms, and this is the Ember force field. Other macromolecular force fields exist too, like the charm, or PLSA, or Bromos, or MF3. So parametrization of a concise set of chemically unique atoms, underlying hypothesis is the parameters. When you look at here, you need the parameters, right? How do you measure or calculate these parameters? So you need to put that information into the molecular dynamics simulation, right, to run it. So how do you parameterize these parameters? How do you generate these parameters? With which methods would you generate it? What? I could. Equations of motion?
Yes, applying the motion. Starting the distribution from initial state to trajectory.
That's a molecular dynamics
Yes.
simulation, yeah. That's depending on Newton's equations. But how would you calculate a force field? So say for example, the force constant here for bonds, or the bit, or the bond. How would you calculate it? Or how would you calculate R0, which is the equilibrium distance? I cannot believe you. No answer? No one? Okay, how would you calculate theta zero, the angle, equilibrium angle? How would you parameterize these Ember force field parameters? How would you generate? From the PDB, you said. What guarantees you that the X-ray curve the equilibrium distance between two atoms or the angle between three atoms? There is none, right? So I would use quantum mechanics, for example, to calculate these parameters. Or you can go to IR experiments, etc. But I would use quantum mechanics to parameterize them. Doesn't it make sense? Yes, right? Okay. So underlying hypothesis is that parameters describing a given atom are essentially local and may therefore be ported to different chemical environments. So this is quantum mechanics, right? It's MP2 level of theory, which I didn't explain. But here you have, let's say, the chain. And you can calculate the distance between the carbon-carbon atoms, for example, right? And which one is the equilibrium distance here? The minimum, yes. Yes, the minimum. Okay, so a harmonic potential is used to estimate it in molecular dynamics simulations. And it looks a little bit better, but catches the minimum, as you can see, right? So it catches the equilibrium value. So torsional potential, dihedral angle for atoms, torsion is another name. So it looks like this. And again, the minima can give you the equilibrium values. So modeling the electrostatic contribution, how would you do that? How would you calculate the charges acting on each atom? The charges of atoms, how would you calculate? Could you use quantum mechanics? Yes. Yes. You did that actually yesterday. So, in CHARM, the electrostatic and CHARM parameters, Martin Farkus's CHARM program and CHARM parameters, the electrostatic term is parameterized from intermolecular interactions. That means quantum mechanical calculations are performed for the interaction. You have the molecule in water minus the molecule energy minus water energy at the same level of theory. So how would you calculate the van der Waals interaction parameters? It's the same, right? I would prefer quantum mechanical calculations. So this is the estimation that we have. Transferability of parameters constitutes one of the key assumptions of macromolecular force fields. The underlying idea of macromolecular force fields is a minimalist description of complex chemical objects based on a limited number of terms, often add up. Parameterization of different macromolecular force fields rely on distinct philosophies. Parameters are not interchangeable between different potential energy functions. So, when it comes to force field parameterization, determine bonded terms. I would do gas phase quantum mechanical calculations. Determine electrostatic term, gas phase quantum mechanical calculations. Determine van der Waals term. You can add the liquid effect here. Some don't. determine torsional term, which is the dihedral term, gas phase QM calculations, quantum mechanical calculations, and from there on, you can have the force field. And McCarroll and Martin Karpus did amazing jobs in this area. So if parameters are missing from the force field, which is usually the case for some ligands or metals or so, then if you cannot parameterize that using quantum chemical calculations or quantum mechanical calculations, the following philosophy of the force fields is option one, parameterize them using quantum mechanics, or turn to a more comprehensive force field, OPLS, okay? How do you do that? If parameters are missing from the force field, you can develop OPLS parameters by using CGen effect. Right, Nisa? So CGen effect is a very easy to use server relying upon ad hoc inferences and educated guesses of missing parameters. And it's like the Swiss parameter page CGen FF, where you can download it even for bromance. So there are different water models. It's one of the most widely existing molecules. It's the most widely existing molecule and one of the hardest to model. The main culprit is the electrostatics of water molecules. In simple 3-point charge model, you have a yield and error of about 50% in the regeneration of the potential. This error drops to less than 10% with a 4-point charge model. What is a 4-point charge model? What is a 3-point charge model? Yes, I'm listening. What is a 3-point charge model? You have 3 centers. So what is a 3-point charge model? You have the hydrogen, oxygen, and hydrogen. But the oxygen is electron, long.
2, 3, 3.
How many?
So, okay.
How many electron lone pairs are there?
2, 3, 3.
Yeah, you have 2 electron pairs. And you can assign them as a center 2, a different center 2, and then you are speaking about a 4. You are speaking about a 4-point charge model. So here, most force fields were developed with 3-point charge water models. Our SPC, you use TIP3P in your molecular dynamics simulations just recently, but there's also TIP4P developed by Jorgensen and co-workers, or TIP5P, whereby you treat each electron pair as a center, okay, on the oxygen atom. It's very interesting. So actually, before we continue, I would like to explain you a simple story. While I was at Stanford, Anders Nielsen, my advisor, came up with a water model. Not theoretically. Theoretical calculations like Coskuner-Weber with the dynamics. Well, but he did experimental study. And he found out that there is no whiteboard on blackboard here, so I need to draw it here again. He found that the water molecules arranged in a spherical so it looks like this with more water molecules. Okay, spherical wave and hydrogen bonding is occurring between them, right? And then at the same time, do you know the story between Berkeley and Stanford? They fired him. There's a big. So Teresa Hedgarden fired back and said, this is wrong. And the odor molecule arrangement is like this. So with different hydrogen bonds and so this is still not solved. Nobody won the race. This is still not solved. Nobody knows what's going on. Water is very difficult to study because it's a very dynamic system, right? And so these classical 3-point or 4-point charge models or 5-point charge models. While 5-point charge models are giving better results at some properties than 3-point charge models, but it's difficult with water molecules. So towards a simpler representation, you can use in molecular dynamic simulations all atom models. So you can treat each atom. In the united atom model, for example, to take CH3, for example, when you have CH3, it looks like this. I wish we had a whiteboard or a blackboard. So deriving the equations would be easier. In all atoms, you have the carbon, hydrogen, you have red for CH3. In united model, CH3 is a sphere. So, okay, in coarse-grained model, let's say the unit, it can be an entire amino acid process. All right? So you can study larger size systems with coarse-grained simulations rather than dynamic simulations, but the models are simpler too. So the approximations are higher too. And if atom types and parameters are missing from a macromolecular force field, one ought to follow verbatim in its philosophy to update it. A force field is a very fragile construct. Its elementary bricks cannot be swapped without any precaution. The vast majority of macromolecular force fields are pairwise additive, meaning they do not account for true space induction phenomena nor of charge transfer. To reduce the computational effort and access longer timescales, the atomic description can be coarse-grained. One should, however, not simplify a model until one understands fully the phenomena at play. So, when it comes to the propagators of molecular dynamics, you can use the leapfrog propagator. This is the equation that is used in the leapfrog propagator, for example, to determine the velocities and positions. Well, here we have the velocity Birlett propagator. This is also time reversible, as you can see. And here the velocity is determined in this way. So the integration, oh, thank you. Thank you, but I'm almost done. Yes, tomorrow it will be very useful. The integration of the equations of motion generally relies upon a Taylor expansion of the positions, possibly the velocities at t plus delta t or t minus delta t. While in some algorithms, knowledge of the velocities is not mandatory, the latter are required for the determination of the kinetic energy. The cost of the simulation can be reduced turning to a multiple time step integrator, which exploits the fact different degrees of freedom relax over different time scales, and thus can be updated at different frequencies. So when it comes to restraints versus constraints, the concept of biased molecular dynamic simulation. So what is that? Here, when you look at the graphic, the delta G here, you have a very high energy barrier, right? Right? So to push back the limitation of brute force molecular dynamics and excess time scales not amenable to conventional simulation times due to significant free energy barriers, we have the concept of biased molecular dynamic simulations to work. This means adding additional forces to the conservative forces arising from the force field will result in preferential sampling of slow degrees of freedom ordinarily poorly explored in standard simulations. And here are the papers to read, actually. And when it comes to restraints, the idea is we want to reduce the volume of the configurational space to be sampled by means of geometrical and harmonic restraints. And we can stacking in geometrical free energy calculations as application area. So when it comes to the role of geometrical restraints, the steered molecular dynamics, how many of you know what an atomic force microscope is? Atomic force microscope. Have you ever heard it? No? Yes? What is it?
So there's a structure which is like it's so we use a force field where atoms apply to yes. Then yes, that we see the material structure, but it's not malfunction. STM or transitions.
Yeah. Thank you. So AFM is very important. For example, you can, in this case, you are interested in the strength of the material or what?
Yeah, the strength. Sometimes I forgot the color. There are 3 types of.
So AFM, atomic force microscopy, you pull that bit of force, okay? Let's say one end of the protein is pulled by a force. And then you start measuring if the thread ruptures or not. Okay? So that force, you can do that experiment, you can do that in molecular dynamics simulations too, and it's called steered molecular dynamics. The external force is exerted onto the system to force it to drift along the desired direction of the Cartesian space. In constant force steered molecular dynamics simulations, a constant force on the order of 10 to the minus 12 to 10 to the minus 9 unit is exerted onto a subset of atoms, in addition to the conservative forces of the potential energy function. So this is an additional force. And it has to be at constant velocity. You have to do the experiments also very carefully. So this is to mimic the action of a mobile cantilever acting on a substrate in AFM experiments. And if you are interested, you can look into that too. It's very interesting. At Johns Hopkins University, people did AFM experiments and also we did the simulations actually. So the role of geometrical restraints when we give another application area, molecular dynamics, flexible fitting is another application area. Here you fit the atomic structures into density maps. The method consists of adding external forces proportional to the gradient of the density map into a molecular dynamics simulation of the atomic structure. And this is also a combination of high-resolution atomic structures with low-resolution chiroelectron microscopy maps that result in atomic models representing the conformational state captured by chiroem. Okay? So if you want to complement chiroem experiments, this is the way to work with it. So, and then we have holonomic constraints. I don't want to talk about it. You are very tired of equations. So, which assemble should the simulation be performed? So, any idea which assemble you should use for biology? Would you use, let's come back to the assembles definition. Yeah. Would you use the grand canonical assemble? Why not? Huh? Yeah, fine. Okay. In how many biological systems is the energy or chemical potential constant? Certainly there are systems where there are constant, but it's not that much the case when you simulate a water, when you simulate a protein and water, or a DNA or a carbohydrate complex for liquid to water, etc. Right? So usually we use canonical and isothermal isobaric assemblies. So yes. What time is it? So the concluding remarks are, it's a computational microscope. In recent years, molecular dynamics simulations have become an important tool to complement experiments, offering unprecedented resolution to access to valuable dynamic information. The inherent parallelizable nature of molecular dynamics makes it an ideal candidate for harnessing the constantly growing capacity of novel computer architectures, relating both the size and time scale tackled by simulations. Molecular dynamics rests on the equations of classical mechanics and the use of empirical potential energy functions, the construction of which relies on stringent assumptions and approximations. As macromolecular force fields become more sophisticated and thus less tractable, accounting for induction and charge transfer phenomena, one must choose between longer simulations with a more appropriate description and shorter, more accurate simulations. So, this is the end of molecular dynamics. Let's have a wrap up. So some of you could conduct molecular dynamics simulations. I'm very happy about that. So to practice on them, very useful. Some of you learned the theory behind that. That's very important. Some of you understood the connection between quantum mechanics and dynamics. Very related. And are there
when we are selecting water for the system, why not physiological buffer? Physiological buffer. Physiological buffer.
can use a physiological buffer? But most of the systems, like biological systems, how much your body is made of.
Mostly they are not if you use water, so there would be the cell will be inside. Water state the cell. In the cell, there's an impossibility to get the cell. So the best way I think is assured within the radical.
You can use a physiological buffer too.
Simulation and variability.
You can do that. You can use continuum models. You can do that explicitly as much as you can. And how can we do that physiological buffer? Because physiological buffer changes from environment.
No, we normally consider perceptual But any kind of cell, we use just 0.9 nanometers, sorry, 0.9 nanometers for fluorescence. Almost every cell. So you can escape the medical problem. The solution we can take.
Yeah, exactly.
Like mostly we are hitting cell, we just make a solution of 0.9 normals NaCl solution.
We have to.
Sodium chloride, yeah, or
I
now
have that.
we use, this is a physiological buffer, and in this case, any kind of cell is not harmful, right? It's a small. I mean, this is solvent system, cell is not damaged by the buffer in normal. So if you consider the same thing for simulation and for the other thing,
You can also add sodium chloride on the simulation. As a buffer.
Yeah, exactly. Right? I don't understand.
You can add sodium chloride.
You can add
I mean-
potassium bromide, you can add sodium chloride, you can
instead of
add
water.
calcium. You can add anything you want, more of it. So, because I don't understand the function.
I mean, if we just consider water as a solvent, so if there was some.
When I say in
temperature
water,
difference-
the ions are included. Example, ions. So. Okay, any other questions? All right, thank you very much. Yes, sure.
Shall we also get the slides of quantum yesterday?
Yes, sure. I thought they wanted to upload it yesterday.
But it's
The three of them.
Sure, we can upload them. So. Are there any questions online? I don't see anything like.